started?
Yeah.
Are you sure?
Yeah. Button press.
So last time we did 5.3, which some people have been complaining that 5.3 is the hardest section that they've done so far, right? And that's probably true. There's a couple more pretty rough ones to come in chapter 6, and then it actually kind of starts to taper back off a little bit, where you sort of get the hang of the probability, and then we're not doing probability problems anymore. We're more applying them to a broader range of stuff, and that's a little bit easier. So any questions over section 5.3? That homework is due tonight, by the way.
Is that?
It is up, yeah.
Okay.
Well, I did get one email from a student last night that said, hey, it's locking me out for some reason. It showed the due date was still not passed, but it still wouldn't let him in it for some reason. So there must have been some, like it was down maybe for a while or something, but yeah, it should be up.
It's working.
You just did it? Okay. Okay, so before I start today's lecture, I'm gonna actually show one of the Course Compass homework problems out of 5.3. How many people have done 5.3 already? Most of you. So you remember this problem. This is the one that says, in 3 independent flips of a coin, where there's a 55% chance of flipping ahead, let A denote the first flip is ahead, B is the second flip is ahead, and so on. Okay? Well, I want to start with that. For those of you that haven't done it, this should help you do that problem, but it will lead us into today's section as well. So if I have 3 independent flips of a coin, then I can represent that as a tree diagram with heads, tails for the second flip, and then heads, tails for the third flip. And how many branches are there? 8 of them. 2 times 2 times 2. 2 to the third or 8, right? Now, on a tree diagram, we showed last time how you can put on there the probabilities, and it says we have a 55% chance of flipping ahead. So what's the chance of flipping tail? 0.45. Because within any group of branches, they have to add to 1, right? Now, one of the examples we did last time, the probabilities changed as we went across the tree. And those were dependent tries, right? These are independent, so the probabilities remain constant. Okay? So I can just fill in my 0.45 all the way across, and my 0.55. And I'm not going to do the whole darn tree, but we'll do the top half of it through at least. So let's look at this last one where it says event D denotes 3 heads on the first 3 flips. Okay? What's the probability of D? Well, that's the same thing as heads, heads, heads. Right? How do I get that probability? Okay? You just multiply the probabilities along that branch of the tree. Right? So that's 0.55 times 0.55 times 0.55, because that's the branch H, H, H. So that's 0.55 times 0.55 times 0.55, which is 0.55 to the third power. Right? Not too bad. What is it that we're doing when we multiply the probabilities? We're finding the probability of an AND statement or an OR statement. It's an AND statement. The word AND goes with multiplication. Why is this an AND statement? I don't see the word AND written in there anywhere. The first 3 flips have to be H's, so another way to say that is the first one has to be an H, and the second one has to be an H, and the third one has to be an H. Even though they didn't write the word AND in there, it's still an AND problem. So you have to learn to recognize that, right? So, probability that I get 2 heads in 3 flips. That's not one of this problem. In fact, I can go ahead and shut that off. How would I do this? Probability of 2 heads in 3 flips.
Is it at least 2 heads or
Nope.
only 2 heads?
Exactly 2 heads. I do want to do an at least one, but I might not get to that today. But that you do, it's similar. Exactly 2 heads in 3 flips.
You have to go through
It's
the tree.
heads, it's tails.
See how many times you have 2 heads and 1 tail.
Okay, good. You have to go through the tree and see how many times you get 2 heads and 1 tail. So heads, 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 that one doesn't work. Heads, heads, tails, that one does work. So heads, heads, tail. Right? That's 2 heads. Where else do I have that happen?
Heads, tails, heads.
Right here, heads, tails, heads. What about this one? No, this one?
Yes.
Yes. So that one, tails, heads, heads. And then that's it, right? So there's 3 of the branches that have 2 heads. So what's the probability of 2 heads in 3 flips?
3 of 8.
What's that? 3 out of 8? I was hoping somebody would say that, so I could go, eh. But that's a good first guess. 3 out of 8. If this were a fair coin, you'd be absolutely correct. It's not a fair coin though, so these branches are not equally likely. So how do I find it? Well, what's the probability of all 3 heads? 0.55 cubed. We already did that one, right? What's the probability of this branch right here? Okay, 0.55 times 0.55 times 0.45. Again, you multiply the probabilities along the tree to get to that branch. So what's the probability of this one? Same thing, but the 4, 5 is in a different place. But multiplication is, what's that word? Commutative. Multiplication is commutative. So this probability is going to be exactly the same as those, right? So somebody give me this as a decimal. Point what? 136. Exactly? Or is that just rounded to 3 places? 3, 6, 1, 2, 5. I'll go to 4 places. Okay? And then this one is going to be the same thing. And this one's going to be the same thing. So let me ask you again. What's the probability that you flip this coin 3 times and you get exactly 2 heads? Is it 0.1361? Morgan, you went, no, it's not. 2 heads and 3 flips.
All those have 2 heads.
All of these have 2 heads. So, is this an and statement or an or statement? It's an or statement. Because I can get 2 heads on this branch, or on this branch, or on this branch. When you say the word or, you do what? You add probabilities. So I'm going to add those 3 probabilities together to get the total probability. Now each one of these alone is an and statement. So this branch is heads and then tails. But to get 2 heads doesn't specify order, so then it becomes an or statement. I can get this branch or this branch or this branch. So I sum those 3 probabilities, which notice that they're all the same, so that's the same as doing what? Multiplying by 3, not cubing it. Don't get too excited about cubing. So it's 3 times that. Somebody give me that as a decimal.
0.4084.
0.4084. .4084. Okay, so that's this answer times 3.4084. So there's about a 41% chance that I'll flip this coin and I'll get 2 heads out of the 3 flips. Okay? Well, see if you can do the probability of 2 tails. What's the probability of exactly 2 tails in 3 flips? And I'm skeptical that you can do this in your head, so you better pick up your pencil. And you probably can't do it without a calculator. At least I couldn't. And we will be using our calculators. I'm going to teach you some things on them here in a little bit. So, I'm going to erase my clutter over here. All right, I'm going to walk around and see what you got. Okay, that's going to be exactly what you got. Let's see. Okay, so, and tell me what numbers you multiply. And all 3 branches are going to have that same thing. They're just being in different order. Got anything yet? Yep, you're getting there. You got the, that's right. Now, how many branches have that probability? Yep, that's right. What I'm seeing is 0.3341. Everybody getting that? Okay. So the first thing to do is to identify how many of the branches make that true. Exactly 2 tails. So top one no, second one no, third one no, but this one does. So that's heads, tails, tails. That probability is 0.55 times 0.45 times 0.45, right? Then we keep going, we got to get 2 tails. So this branch, tails, heads, tails, and this branch, tails, tails, heads, and those are the only 3. So again, it's 3 times this number, but this is 0.11 something, right? So this probability is 0.33, was it 41? 41? Okay. All right. This is exactly the same thing. Getting 2 tails is exactly the same thing as getting how many heads? Right? Same thing. What's the probability of 0 heads? That's the bottom branch, isn't it? And there's only one of those branches. So it's 0.45, 0.45, 0.45. And what is that number? 0.45 cubed. By the way, do you know how to use the raised to a power thing on your calculator? There's a little button that has that symbol. I call it a hat. I think they call it a caret. Right? So it's, you would enter 0.45, hit that caret button, and then a 3, then enter. And what is that number? Anybody?
0.0
0.0911.
to 5.
Okay. To 4 places, that's where I'd stop. Okay. Well, what we're building here is a whole new thing. I think I'm done with the tree diagram. As soon as I erase it, oh, I want that back. But here we go. I need the board space. Let x equal the number of heads in 3 flips. Okay? Then x is said to be a random variable. So we need to define random variable. What does random variable mean? This is actually my favorite definition in this class because it's the most complicated. Right? So here it is. You ready to write this down? A random variable is a variable that's random. See how complicated that is? Now nobody ever is very satisfied with that definition, but really that's all it is.
Can you say it again?
Can you repeat that? If you don't like the way I said it, the book says it like this. It's a variable whose value depends on chance. Oh, you mean it's random? Yeah, it's a variable whose value is random, right? So value depends on chance. So if we let x be the random variable, number of heads in 3 flips, then let's make a little table and write down all the possible values that x can take on. How many heads can you get in 3 flips?
3.
You can get 3. Is that the only value x could take on?
9.
You could get 0, 1, 2, or 3 heads, right? And those are represented by the different branches. So 0 heads was 3 tails. Tail, tail, tail. 1 head, 2 heads, or 3 heads are the only possibles, right? If I write out beside each of those p of x, then I'm saying the probability of that value of x. So it's kind of shorthand notation for probability of 0 heads. I can just say probability of 0. Probability of 1. So what is p of 0?
Like
0.0911. Right? We already did that. So 0.0911. What's the probability that x is a 1? Exactly 1 head, 0.3341. Right? Exactly 2 heads. We did that one here. Exactly 2 heads in 3 flips is 0.4084. And finally, we haven't done this one yet. What's the probability that x is a 3? 0.1664. And how'd you get that? Good. 0.55 cubed. Because that's the top branch of the tree. Heads, heads, heads. And it's 0.55, 0.55, 0.55. So 0.55 times itself 3 times, or 0.55 cubed, is 0.16, and I already forgot what you said. 64. Okay? What we have just done here is write out the probability distribution of x. Okay? So that's a new term for you, probability distribution. You're used to the word distribution. You think histograms, right? think shape of distributions and all that. Well, those kind of distributions are distributions of the population for some variable that we collect, like height or pulse or whatever. We form a distribution. Well, this is a distribution of the probability across the possible values of some random variable. So how much probability is there to distribute? I'm going to take the total amount of probability and I'm going to distribute it across all the possible values of x. How much probability is there to distribute? 1 or 100%, right? So I've taken the number 1 and I've distributed it. Sum these 4 numbers up for me. I'm done. I did it in my head. I'm done. Hey, I'm pretty good, aren't I? What do you get? You get 1.0000, right? I had to confirm that the last digit was in fact a 0. 442 or 4411 gives you 0. Because sometimes it won't sum exactly to 1. It might be off because of rounding, right? If you stop at the 4th decimal place, one of them may round, and you might get 0001 or 9999, something like that, right? So you might be slightly off from 1, and if you are, don't be concerned about it. But if you're off quite a bit, like if you sum these up and you get 0.87, then you know, ooh, I missed one of the possible values of x. I'm missing some probability there. Or you just did one of them incorrect. If you sum it up and it's bigger than 1, then you definitely did one of them incorrect. Right? You've got something wrong in there. It has to add to 1. So one of the rules of probability distribution is that the sum of the probabilities, remember the Greek capital sigma, it means summation? The sum of the px's has to be 1 because you're distributing the total amount of probability. Also, each value of probability in that table has to be between what 2 numbers? 0 and 1. You can't have a probability that's bigger than 1 or littler than 0. So on the next exam, if you do a probability calculation and you write down a number that's bigger than 1, please take a moment and go, wait, that can't be right. Probabilities must be between 0 and 1. You can't have a negative probability. So they have to all be between 0 and 1, and they have to add up to 1 to be a probability distribution. Okay? That's true in this case. They're all between 0 and 1, and they add up to 1. So this is a probability distribution. Now you can graph a probability distribution just like a histogram, just like a distribution of the population. If I define, this is a, by the way, I forgot to say this, this is a discrete random variable, the way I've defined it, because it cannot take on fractional values. If I'm counting the number of heads, I can't get 2.3 heads. I can only get 2, or I can get 3, or I can get 0 or 1. I can't get a fractional number. Right? If x was a continuous variable and a random variable, then we have what's called a continuous probability distribution. That's section 6.2. Right? Today we're doing discrete distribution. Okay, so now back to this. We'll graph this. At 0, I have 0.09 probability. So we'll make that tall. So this is 0.0911. The next one is about, well, a little more than 3 times as tall as this bar. So 1, 2, 3, and a little bit more. I did that pretty accurate. And the next one is even taller than that. It's a little more than 4 times as tall. And then the last one is 0.166. So that's about right there. Just like population distributions, you still have the same idea. Is this a symmetric distribution? Is this a bell-shaped distribution? Is it skewed? Those kinds of questions. Okay? What would you say about this distribution? It's fairly bell-shaped, isn't it? But not perfectly. It's not perfectly symmetric. If it were perfectly symmetric, then these two bars would be exactly the same height as these two bars. What would I need to change in this scenario to make it a symmetric distribution? Change about my coin. Have it be a fair coin, a 50-50 chance of heads, and then you'll get, notice that getting 1 out of 3 heads will be exactly the same as getting 2 out of 3 heads when they're equally likely, because when you do, I've erased them all, but instead of 0.55 times 0.45, you have 0.5 times 0.5, so then it doesn't matter which is heads and which is tails. The only thing then that matters is how many branches of the tree there are, because the branches would all be equally likely. Okay? So that's a discrete probability distribution. One thing that's fun to do on an exam is to give you this. Here's a probability distribution. What's the probability that x is a 1? And I don't tell you anything else. I don't tell you it's a coin flipping problem or anything like that. Just, what's the probability that x is 1? How would you find it? By subtraction. Add these up, subtract from 1, and the missing probability. I couldn't erase 2 of them, right? Because then you can't get it by subtraction. Or another fun thing to do is to go 0.5280 and say, is this a probability distribution? And the answer would be no, it's not, because they sum to a number greater than 1. Right? So it's not a probability distribution. And now I forgot what the real number is in there. What was that? 3341. So now it is a probability distribution. Okay? If I give you a probability distribution like this, I could ask a question like, what's the probability that x is greater than or equal to 2? You're shaking your head at me like, I can't do that. But actually you can. Is this an and statement or an or statement?
And?
I heard the word and the word or said simultaneously. So yeah, that's right. One of them. Which one? How do I get x greater than or equal to 2? I either get x2 or I get 3. When you say the word or, you add the probabilities. So that this is 0.4084 plus 0.1664, which is 0.565748. Doing math in my head on the board is always a dangerous thing, so check my math there. So there's a 57% chance that when you flip this coin, you'll get at least 2 heads. Right? At least means 2 or more. So get ready for test questions where they ask you things with at least in it. And then you just have to figure out, oh, well, I know what that means. And then I just sum up the ones that make that true. Okay? Now, I guess I can get rid of this. Probability distributions, whether they're discrete like this or continuous like next time, they have a mean and a standard deviation. Just like population distributions and data distributions have means and standard deviations, so do probability distributions. And it has the same interpretation. What is the interpretation of the mean of a distribution? Okay, it's the average. So what do you think the average value of x is? This says the mean of the random variable x. What do you think the average value of x is? Well, I heard a wide range of numbers there. I heard 1/4, I heard 0.25? Is that what you said? 0.25?
1.5.
Where'd you get 1/4 and 0.25 are the same thing? Where'd you get that number?
Line by line.
Oh, so you took the average of the probability.
Yeah.
So you added them up, got 1 divided by 4. So, but that's not what this is. This isn't the mean of the probabilities. It's the mean of the random variable x. So what's the average value of x?
1.5.
1.5. No. And what did she do? That's the most common mistake. That's the first thing that people always try. And thank you for always being willing to speak up without waiting for somebody else. She just averaged these numbers, right? But wait a minute. Some of these numbers are more likely to occur than other numbers. So you have to do what's called a weighted average. When we do a simple average, here's the formula for x bar. Remember how to do x bar? Sum of the x's divided by n, right? Which is the same thing as the sum of x times 1/n. Right? Algebraically, that's the same thing. 1/n is the same thing as the whole thing over n. Right? So this is a weighted average of the x's, weighted by how many times each of those x's occurs. And if I got n of them, a sample size of n, then each occurred 1/n, right? Or what proportion of the sample this x represents. That's the way I should say it. What proportion of the sample does each of the x's get? It gets 1/n, right? But here, what proportion of the population does a 1 get? 33.41, right? So I can do this same thing, but replace the 1/n with the probability of getting that value. So the mean is the sum of each x times the probability of getting that x. And then sum them up.
Sum of each x.
Times its respective probability. That's another way to say it. So let's compute that for this probability distribution. Because even when it's written out there as a formula, most people look at it and go, I have no idea how to compute that. Is that what you were thinking, Aaron? So each value of x times its probability and then add them up. So here's how we do it. Just stretch it all out. I got 0 times 0.0911 plus 1 times 0.3341 plus 2 times 0.4084 plus 3 times 0.1664. You remember taking the mean of a frequency table? It's exactly the same idea. You have a frequency table, only instead of probabilities in here, you had numbers. That this one occurred, 21 times, and this one occurred 58 times, and so on. Right? And I said, well, you have to do a weighted average. You have to weight by how many times each one occurs. Same exact thing here. Right? Only when you did it with a frequency table, you then divided by the overall n. Well, that's exactly this, because if I have a frequency of 21 times and I divide by n, now it's turned into a proportion. Right? So it's the same thing. So somebody do this on your calculator for me. Tell me what you get. I thought you'd be playing along and already have this done.
I got 1.65.
1.65. Go ahead and give me 4 decimal places. 01? Like that? Okay. Does that make sense? I've been harping on you, and I'm going to continue to harp on you that anytime you write the answer down to something, look at it and go, does that look about right? You won't catch all your mistakes that way, but you'll catch the big ones, right? If you got an answer of 0.16, you ought to be able to look at it and go, well, that doesn't seem right. Look at this. Remember where the mean is when you have a histogram? Remember what I said? It's the balance point So if I cut this out of a piece of cardboard and try to balance it, where is it going to balance?
Closer to 0.
If I put my fulcrum right there, this thing won't fall over?
Well, I mean, like between 0 and 1.
There?
Because this side is heavier than that side.
Yeah, so it wouldn't balance.
Oh, I don't know how to balance.
Closer to the 2? Okay. All right. Think about this line is the teeter-totter, and these are kids, and the height of the bar represents how much that kid weighs, right? So where's it going to balance? Well, if I put it right exactly in the middle between 1 and 2, at 1.5, which was our first guess for a mean, which side is heavier?
2, 3.
These two bars are both bigger than these two bars, right? So I need to go which way? I got to go that way towards them, right? Because remember, to balance a little kid and a big kid, the big kid has to be closer to the balance point. So this is the big kid. So I got to move my balance point towards the 2. But I'm not going to go all the way to 2, so it's going to be a little bit to the right of 1.5, but not a lot to the right. Because it isn't that much difference in the weight. So 1.65, does that seem about right? Yeah, makes sense. Right? If you got 0.25, one of our first guesses, you should be able to realize, well, that can't be right. Once you think about balance, point, and all that. Okay. Okay, now I want you to compute the standard deviation of this. Okay, it's kind of a trick question. That's a bear to do by hand. Right? To do it, remember standard deviation of a sample had x minus x bar, quantity squared, divided by n minus 1, blah, 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 and then the square root of that. Well, it's the same thing here, but it's the square root of the sum of x minus the mean of the x's squared times the probability of the x. And all of that's under the square root. Right? I really don't care if you know that formula or not. I will not make you use this formula all the way out by hand. It's built into the calculator. And I can read lips, Erin. And she did this. Can you read lips? Thank God. That's right. It's built in the calculator. So let's do that. Let's get our calculator to do that. And I'm going to pull that down that far and turn on the projector. And pull up my TI-84 simulator here. And if I'm just wanting mean and standard deviation, you should have already in your head that, oh, we usually do that with which function on the calculator? 1-bar stats, right? So you're going to do that, but you're going to do it the same way we did it when we had frequency tables. You put the x's into L1, and you put their weights into L2. And this time, the weights are the probabilities, not the frequencies. Okay? So I just want x's in L1 and probabilities in L2. Right? So, I've got some other stuff left over from before. Let me clear out that, then go to my list editor. And my L1 is in there already, but my probabilities aren't right for this problem, so I need to fix those. So just enter them as I'm doing that. Do it in your own calculator. Now, who remembers how to do mean, standard deviation, and median, and all those things with the 1-bar stats when you had the two lists, L1 and L2? What do you do? Yeah, L1, comma, L2. So, first you click the stat button. Then you go over to where? Over to calc. select one of our stats by just pressing enter, and then put L1, comma L2 right there. So second function L1, hit the comma button, second function L2, and then hit enter. So it says X bar is 1.6501. Exactly what we got here. Right? It also tells us that sigma X is 0.861666. Okay? That's this. Now, how do I know when to use Sx and when to use sigma X? If it's sample data, you use Sx. And I told you before, we almost never will use sigma X. And when I said that, you probably don't remember this, but I said there's one time this semester when we will use it, and that's today, right? Probability distributions. So probability distributions are the only time that we use sigma X. And conveniently, it doesn't even give us Sx. It leaves it blank. Now, how is the calculator so smart to know that I didn't want Sx for this problem? Well, it's not that smart, but look what it says the sample size is. 1. And how does it get the sample size? It sums the weight column, right? And it summed it up and said, well, there's 1. And what does the formula for sample standard deviation have on the bottom of the fraction? N minus 1. It has a bunch of ugly stuff over n minus 1, right? And then square root all that. So you get undefined, so it just doesn't compute it. Which is fine, because we don't want it this time. We want sigma X. So what does that number mean? 0.86166. Interpret that number for me. What did standard deviation mean in a population distribution? How did we interpret it or use it for interpretations? Okay, it's how far from the mean we go in order to get a certain percentage of the population, right? So if I go plus and minus 1 standard deviation from the mean, I ought to have 68% of the population, right? That works for bell-shaped symmetric distributions. This one's reasonably bell-shaped and symmetric, so I can say something like that. Only now instead of talking about percent of the population, I talk about of the probability. So 68% of the probability is going to be within 1 standard deviation of the mean. So the mean was 1.65. Go 0.86 to the left of that, 0.86 to the right of that, you capture. Most of the time, the way we use it is a little less detailed than that. We'll say things like, would a value of 0 be considered unlikely? And you say, well, let's see how many standard deviations away from the mean that is. And if it's 3 standard deviations away from the mean, you say, yeah, that's very unlikely. Okay. So it'll be questions like that. Okay? All right, I have 5 minutes left, which is just enough time to do an example problem that will be on your homework. Oh, I forgot to say one thing. This mean of a probability distribution, when we do the mean of a probability distribution, it has a special name. We call it the expected value of the random variable x. Expected value. Now, depending on your perspective, that's either a good name or that's a bad name. And it's kind of a bad name because when I flip a coin 3 times, I don't expect to get 1.65 heads, right? I'm either going to get 1 or I'm going to get 2 or I'm going to get a whole number. But you can't think of it that way. You have to think of the long run probability. So if I repeated that experiment 1,000 times and averaged the x value that I got from those 1,000 times, I would expect it to be real close to 1.65. So it's the expected value of the average. Okay? So, having said that, let's go play the lottery. let's play pick 3. Now, the one that's in the book, I think he says is the Ohio State Lottery. And Kansas pick 3 is probably similar, but slightly different. But pick 3, you pick 3 digits, and then you hope that they pick the same 3, and if you match, then you win $500. Right? Well, how many possible numbers are there that you could pick? And it's sampling with replacement. So you can pick the number 333. Well, how many digits are there? That's not a trick question.
How many digits do they allow?
0 through 9, right? And that's 10. So I got 10 ways to fill in the first blank, 10 ways to fill in the second, and 10 ways to fill in the third. So the total number of possibilities is 1,000. Right? So what's the probability you win on one play? 1 in 1,000. Right? You can also think, alternatively, you can think of it as pick a 3-digit number between 0 and 999. And there's 1,000 numbers there. If you match their number, then you win. Right? So if you win, you get $500. So let's let the random variable x represent your winnings. If you don't match, you lose, which means you don't win anything. You win 0. So this is lose, x is a 0. If you win, x is $500. Okay? This is a probability distribution with only 2 possible values for x, 0 and 500. Now we need to list the probabilities for each of those. What's the probability? Let's do the win first. We already said that. Probability of win is 1 in 1,000. So that's 1 over 1,000 or 0.001. So what's the probability you lose? 999 out of 1,000. So 999 over 1,000 or 0.999. Right? Now, the big question on a problem like this is always, what's your expected winnings? What are your expected winnings when you play this game?
$500.
If it was $500, if that was the expected value, I'd be playing as often as I could. What does expected value mean? It means the mean. So what they're asking is this. So I got to sum up each value of x times its probability. So the first value of x is a 0. I'll do that one. 0 times 0.999 is 0. Plus 500 times its probability. Okay? So what do we get? You can do this in your head, actually. My 6th grade daughter is coming home with math problems like this. And you just have to know, well, I just move the decimal 3 places, right? So my decimal's here, I got to move it 3 places, and I get 0.5. And this is in dollars. So my expected winnings are 50 cents. Right? Hey, that's not bad. I'm going to play. I win 50 cents every time I play.
But how much does it cost you to play?
How much does it cost? Well, it costs $1 to play.
Oh, see, what are you really not winning?
So you're really losing 50 cents. You expect to lose half of whatever you pay to play. And that's actually the way most lottery games work. They give out half of what they take in as prize money. The other half they build bridges with or whatever. Right? So you expect to lose half of what you do. All right. It is Friday before fall break. So we'll see you next Wednesday. Have a great fall break. This homework, section 5, section 6.1 is due that Wednesday that we come back at midnight. Okay? And tonight by midnight is 5.3. All right, we'll see you then.